Okay, we're live. Good evening, everyone. Thanks for joining us. I'm Rich Ozer. Here's Gerald McKeegan in the other frame. We're also honored to have John Curry with us tonight, who is learning some of the technology, and he'll be curating some of your questions. And we may let him even answer some of them. We'll see. So we're going to get started by talking about what's on a lot of people's minds. Gerald has prepared a little bit of a discussion on comets, and we've got some photos to show you, and we'll go from there. So, Gerald?
Okay, well, it's a photo that we want to show you. So a lot of you have probably heard that there is a nice bright comet that's been visible for the last few days. The comet is called C/2020 F3, and it's better known as Comet Neo Wise. This comet was discovered by the Neo Wise spacecraft, which used to be called the Wise spacecraft. It's an infrared telescope spacecraft that has been up orbiting along with the Earth. It doesn't orbit around the Earth, it orbits along with the Earth. And it was originally for infrared studies of many other objects around the universe. When it started to run out of its coolant, they switched its function to search for near-Earth objects. So that's where they added the NEO, which stands for near-Earth object. So it's now known as Neo-WISE. And it discovered this comet earlier this year. The comet is now relatively close to us, and it has been visible in the morning. And so if you are up early in the morning, pre-dawn hours, say around 4:30, 5 o'clock in the morning, you'll see it just as the eastern sky begins to lighten. And it's in the northern sky right now. And it is slowly changing position. It's near the constellation Auriga at this time, but it is slowly working its way to the northwest. And in a few days, it will be in the constellation Lynx. And then I think eventually it's going to end up in the constellation Ursa Major. However, it is slowly fading as it gets farther away from us. So if you want to see it, next few days would be a good time to look. Again, right now it's a morning object, but in about a week or so, it's going to be visible in the evening in the northwestern sky. I wanted to show you a picture. I'm not sure if everybody knows, but there is an astronomy club based here at the Chabot Space and Science Center. It's called the East Bay Astronomical Society. And one of our club members is named Bob Miner, and he's an avid astrophotographer. And he was up at Tilden Park yesterday morning, and he took what was a great picture. So I'm going to see if I can share my screen and get that image on here. There it is right there. So this is, again, in the pre-dawn sky. You can see the comet very clearly. You can see its long arcing tail. We don't see much of the gas tail. That arcing tail that you see there, that's primarily dust and particles coming off of the comet. Comets are what we sometimes call icy dirt balls or dirty snowballs. They're mostly ice, but they have rock and sand and gravel embedded in the ice. And as the comet gets close to the sun, that ice sublimates. It goes directly from a solid to a gas. And as it does so, it releases all those particles that are embedded in the ice. And so that long, arcing, whitish colored tail that you see coming from comets is the dust and particles coming off the comet. That's the stuff, if the comet happens to cross the Earth's orbit, that stuff left behind by the comet will become a meteor shower. This one is not going to give us a meteor shower, though it's oriented incorrectly. But this is what it looked like yesterday morning. It'll probably look like this or similar to this for the next few mornings. And then eventually it'll be an evening comet as it moves higher in the sky toward the northwest. So anyway, it's something to look forward to. Best to, if you want to look at it, it's best to bring a pair of binoculars. It's not real bright. With binoculars, you should be able to see it very well. If you want to take pictures of it, you may need to do a little bit of a longer exposure in order to see it, say 10 seconds or 15 seconds. I'm not sure how long Bob exposed this image here. But Comet Neo Wise is out there right now, so check it out. All right.
Thanks, Gerald.
Sure.
Yeah, I want to warn people that you really need to have a pair of binoculars with you, and that way you can scan the sky. And if you're getting up early in the morning in the next couple of days, you want to be scanning the sky right before sunrise. But more likely, you'll probably end up waiting a week and a half and look for it immediately after sunset. And it's a lot easier if you scan the area around the sun where the sun has set. Don't go looking at the sun through your binoculars, but wait for the sun to set and then scan the area of the sky where that sunset took place, and you should be able to see the comet. And then as it gets darker, you might be able to see it naked eye. It was not a particularly bright naked eye object, but it was a remarkable comet to look at because of the size of its tail. I missed Halley's Comet years ago when it came by, and so I think that this is probably the next best thing because of, it's just a classic comet, with a bright core and really long tail. Most of the ones we see tend to be just, kind of a circular disc or just kind of a bright smudge. This really had all the classic features. All right, what's next?
Well, let me unmute myself here. So I think the next thing we want to do, last week we showed you a bright globular star cluster in the constellation Hercules. And I think I mentioned that there are quite a few of these globular star clusters that orbit around our galaxy, somewhere between 150 and 200 of them. And as it turns out, there is another globular star cluster in the constellation Hercules, and it is called M92. It's not quite as bright as M13, the one we looked at last week. It's a little bit farther away, but we've got the telescope pointed at it right now. We do have clear skies tonight, light wind and low humidity, so it's very good viewing conditions. Plus the moon won't be up until after midnight, so we've got nice dark skies. So telescope right now is pointed at M92, and there it is. And you see it's not quite as dense as M13, which we looked at last week. This one is about 27,000 light years away. M13 was around 23 to 25,000 light years away. So once again, these are stars that are very old. They are among the first stars to have formed when our galaxy was forming. So these stars are more than 10 billion years old. The stars orbit around the center of the cluster in highly elliptical orbits. We can't show it to you here. We have a great animation that we do in our planetarium that actually shows how those stars orbit around the cluster. These are very long elliptical orbits, so they swing in very close to the center of the cluster, and then they go around the center, and then they come back out, and they go far out towards the fringe of the cluster. When they're in close to the center of the cluster, their orbit velocity is very fast. When they are far away from the center, their orbit velocity is very slow. So it's swing in, go very fast around the center, swing out, slow down. Eventually you reach the maximum distance, and then you just do the whole process over again. You can't really see it very well, but there are a few blue stars in here. Now, the fact that this cluster is so old means that all of the stars should be yellow maybe white or even orange or red. But we see blue stars, which is confusing to, or was confusing to astronomers for a long time, until they understood that because those stars are so close to each other near the center, they sometimes bump into each other or pass so close to each other that one star can strip off material, the outer layers of another star. And that would expose the inner part of the star, which is hotter than the exterior, and might give it that bluish white color, which indicates that it's very hot. Hot stars are bluish in color. Cool stars are yellow, orange, or red in color. So anyway, this is globular star cluster M92 in the constellation Hercules. All right. So where are we going to next, Richard? How about the Cat's Eye Nebula?
Yeah, we were going to give that a shot.
All right.
Yeah, so the Cat's Eye Nebula is another example of a planetary nebula. We haven't tried this combination yet before with our camera and Nellie, and we'll see what we get out of it. For those who are interested, we're shooting with a Canon DSLR camera, just a T1i camera. Nothing particularly special. It's the same kind of Canon camera you would buy at Costco. Has a special adapter that allows it to fit into the receptacle for the eyepiece. And I'm using a piece of software called Astrophotography Tool to acquire the images and stretch them if necessary. When I say stretch them, it basically is a way of bringing out the dim light, so it's the much brighter part of the photograph, and it basically sets the white point at a much higher level on the histogram than it otherwise would, or rather a much lower level on the histogram than it otherwise would. So that's what that graph is on the lower left corner. I'm able to play with the light levels, and we're working with like 30-second exposures to try to get you an image that is interesting. Okay. It's showing us the previous image still while it counts up to 30 seconds. Okay, so there it is. And the, let me get rid of the stretch here. Hold on.
I'm gonna slew a little north. See if we can't get it closer to the center.
Bear with folks. Okay, I think I need to change the ISO here to something more reasonable. Go to 1600, try it again.
So while he's working on that, let me unmute here. Oh, I am unmuted. All right, so while he's working on, let me tell you about this. This is a planetary nebula. If you've been with us the last few sessions, you know that a planetary nebula is the remnant of a dying star. So this is a star that was once similar in mass to our sun, but it was an older star. As stars age, they swell up. This star eventually became a red giant star, and it got well over 100 times its original size. So if you can imagine our sun in 5 or 6 billion years, it's going to swell to 100 times or more its current size. When the star gets that big, its gravitational hold on its outer layers is not very strong. And you combine that with strong winds being produced internal to the star because of all the convection and the heating going on internal of the star. And you get these strong winds, which can actually blow mass off of the outer layers of the star. So while it's a red giant, it's blowing its outer layers out into space. And those layers that gas expands away from the star. And at the same time, we're exposing the inner part of the star, the hotter part of the star. And also, it's running out of fuel at its core. So eventually, it runs out of fuel, and the fusion process interior to the star stops. And when that happens, the source of the pressure, the expanding pressure of the star, goes away, and gravity takes over, and the star collapses. And you take a star that was once, say, 1 million miles in diameter, and it collapses down to be only about 10,000 miles in diameter. So it becomes highly compressed. It still has a lot of heat left over from when it was a red giant. That heat is now concentrated in that very small sphere, which then becomes extremely hot and radiates a lot of energy in the ultraviolet spectrum. That star, that collapsed star, which is now called a white dwarf, is surrounded by all the gas that was expelled by the star before it became a white dwarf. And the ultraviolet radiation goes out and ionizes that gas and causes it to glow. So what you see here is the glowing gas that is caused by the ultraviolet radiation from this star. Now, it's pretty small. If we put a different camera on here, we could make it a little bit bigger. But you get an idea that there's this little puffball out there in space. And if you do a high resolution image and look at it carefully, it has the appearance of a cat's eye. So it's called the Cat's Eye Nebula. So, Richard, while you're doing that, I'm going to pull up here. I've got.
Let me just see what this 50, I'm taking a shorter exposure because I'm thinking it might bring out that center a little bit more instead of going out the, there we go. Yeah, so what I wanted to point out is you can see in the center of the Planetary Nebula is the region where the remaining white dwarf star is located. And you can see that bright area is actually the white dwarf, and there is some surrounding bright gas as well, which gives it its characteristic cat's eye shape in the center. But if I take a shorter exposure, it gives you a better idea of where that white dwarf star is located with respect to all of that gas that has sloughed off of the star over the thousands of years that this process has been happening.
Yeah, so not to make you feel bad, Richard, but I've got a Hubble Space Telescope image of the Cat's Eye Nebula.
That won't make me feel bad.
Okay, so I'm going to.
It's much more comfortable here than in space.
So I'm going to go ahead and switch here and share my screen, which I guess is going to shut off your screen.
Yeah, go ahead.
Okay. All right. All right. And there you go. That is a Hubble Space Telescope image. It's actually a combination of a visual image and an X-ray image. And this is what the Cat's Eye Nebula looks like close up. And there's a lot going on here. I was telling you about how gas is blown off of the star. That often happens primarily at the poles of the star. The star is slowly rotating, just like the Earth is rotating. The star is rotating. And as gas is being blown off, it comes off of the poles. Now, I don't know if you can see my cursor or not. Richard, can you tell me if you see the cursor? Okay. Okay, so if you look here, you see kind of one circular region here, and then there's another one, and you can tell this second one's kind of in the background. If you turn this thing not quite 90 degrees, maybe 80 degrees, you could actually see that these are two clouds of gas coming off the poles, almost like an hourglass or butterfly pattern. At the same time, you've got another burst of gas that's coming off the equator of the star. So it looks like a torus that's around the equator. So it's quite complicated. This is very common with these types of planetary nebulas. And we call them planetary nebulas because when they were first observed back 150 years ago, astronomers thought that these were clouds of gas that were slowly contracting to form planets. So they gave them the name Planetary Nebula. Later on, we realized that, in fact, these are dying stars, but the term Planetary Nebula stuck. And so even though they're stars, we still call them Planetary Nebula. All right.
That's got to be one of the nicest images of the Cat's Eye Nebula I've ever seen.
Yeah.
I'd hate to see the rest of the cat. But no, that's really tremendous. Well, let me put it back on our software. And yeah, it's not as good as the Hubble, but it's like I said, it's much more comfortable.
All right. So you want to try M22? All right.
Yeah, because that's in a pretty different part of the sky. We're going to go to a bright star first and make sure that we've got the telescope centered on a known object in that region of the sky. And then that gives us some reasonable guarantee that when we slew to M22, it'll be in the field of view. So that's the star Vega. It's a very bright star.
Okay, continuing south. We'll go to Roselhaig.
Yeah, somebody was mentioning that they saw M22 through their 4-inch refractor. Cool.
Well, if they can see it, we can see it.
Yeah, that's right. Pretty good. John, you want to get that centered and then we'll do another sync. That's fine. All right. Next hop.
Well, I think we can go there now.
Okay, so we are probably there. And so I'll take it out of live view and we'll start. Again, we're looking at the last shot we took. We'll take another 15-second shot and we'll see if we'll see what we can see. And then maybe we'll take a longer exposure depending on what it looks like. Good. Okay, we're getting there. That's actually okay. Turn off.
M22 is another globular.
Yeah, if you want to move it over a little bit. I just did. Okay, so I'll take another shot. So this one has a much more obvious mixture of stars. And we'll try, yeah, it's a little tough to try to refocus on this object. And it might have been moving when I took it. So, yeah. Okay.
Move it a little farther over.
Yeah, that's what we're doing.
Are you focusing, John?
No, we don't have a way to focus that.
Yeah, it does. You can focus with the secondary.
Oh, we could.
Yeah,
that's
yeah,
right.
I can focus.
That's right. I forgot about that. Okay, that's pretty good.
Okay, see if I can tweak the focus.
Yeah.
Okay, try it now. Either went too far one way.
Yeah, we'll find out.
Or just right the other.
We'll know in a sec. Yeah, this telescope has a motorized secondary. I forgot all about that. Yeah, that was a little bit better. That's pretty good.
A little farther.
It's up to you. One try. You're seeing the same thing I do.
Okay. One more time.
Okay. Let me know when.
Oh, go ahead.
All right. So anyway, what I was noticing is the different classes of stars here are really distinct. You've got some real obvious blue ones and real obvious red ones.
Yeah, so this globular cluster is about 10,500 light years away, so it's quite a bit closer, which, as you can see, it takes up a lot more of the field of view of the telescope. But it has fewer stars. It's only about 300 to 400,000 stars in it, whereas like M13 may have as much as 1 million stars in it.
This one has a lot more symmetry than the last one we were looking at too. Yeah. You'll notice that so some globular clusters are really symmetrical, others are somewhat misshapen. And you know, I'm thinking that before we leave this region of the sky, we should probably take a look at M4 also, because it's pretty unique looking. What do you think?
Yeah, sure.
It's right below Antares.
Yeah, it's over in Scorpius.
Okay, we're going to look at one more in this part of the sky that's, I think, worth taking a look at.
Okay. All right, you ready to slew? Ready to go?
Go for it.
I got headphones on, so you got to talk. This one's even closer. Yeah, we need to go south a little bit. Yeah. Okay. Try it again. So our telescope is computer controlled. So when we want to point it at something, we just either click on it. We have a star chart on the screen, or we can enter the name of the object in a database, or we can just enter the coordinates in it. However, as we move across the sky, the telescope is not perfectly aligned with the coordinate system on the sky. And so what happens when we make big moves, like we made a fairly big move going from M22 to M4, while we get close, sometimes we don't get right on. And that's why you hear us talking about moving the telescope and sinking the telescope and so on. We're just trying to make sure we get right to the object and it gets in the center of the field of view of the camera. If we had an eyepiece on the telescope and we were looking through the eyepiece sees a bigger part of the sky than the camera sees. So something that looks like it's right at the bottom edge or the side edge of the camera view, if we were looking through an eyepiece, it would be within the field of view of the eyepiece, although it may not be centered in the eyepiece.
So yeah, this has to be a lot closer than M22.
Yeah,
right?
Yeah, because it's obviously it's spread out a lot more. This is only about 7.5 or 7,500 light years away.
And when you look at this one visually through a telescope, this bar of stars that you see as distinct stars in this photograph actually look like a bright line in a standard, telescope with an eyepiece, and it's the most prominent feature. I've never looked at it this far magnified, and it's very characteristically different.
Yeah. All right. What else we want to look out here? Well, right now, the comet is actually, I think right now it's now below the horizon. Well, yeah, so it's below the horizon right now. And even if it was above the horizon, unfortunately, straight north of where we are is the roof of the observatory. So it does block our view of the northern horizon. So even if the comet was a little bit above our horizon, we wouldn't be able to look at it. And if the roof wasn't there, there's a line of trees that is just beyond it, which actually blocks our northern sky view as well. So no matter what, we would not be able to see the comet tonight with this telescope. Interestingly, though, if we went to the other side of Chabot with a small telescope, we would be able to see it. It's the luck of where it is and how we're blocked by trees and the configuration of the observatory.
There was a question about the overall, getting back to M4, but I also want to point out, we'll see other comets. I mean, comets are coming and going all the time. So we definitely won't be seeing this particular comet through this telescope, but as the season progresses, there will be others that we'll try to show you. The question was about M4. Why do we have these characteristic arcs of stars? And it's really a great question. And there's a couple of ways to look at it. It could be due to the mutual gravitational attraction of all of these stars to one another. And gravity can be thought of as something that occurs in waves, kind of like ripples in a pond, and it tends to form circular structures in space over great distances. And Also, the formation of these stars all happened from the same large molecular cloud. That's a cold, dense cloud of hydrogen gas. And as that gas coalesced in different regions, new stars formed. And as they ignited, they blew the dark gas away and became visible to our part of the universe. And that process in and of itself involves not only the consolidation of gas in a kind of a localized fashion that might be having gravitational attraction to other parts of the cloud, but also the blowing off of the gas pushes things around in kind of a circular shape. So star clusters always have these arced circular shapes to them. And it's from a variety of dynamic processes that are just kind of, they're poorly understood, but there's a lot of interesting theories around it.
Yeah, one thing
to add on that?
Yeah, one thing you want to keep in mind also is this is a two-dimensional image of a three-dimensional object. So things that look like they're all lined up, if you were to somehow go out into space and get around to the backside or off to the side, their orientation would look very different. So, it's a bit of an optical illusion in some cases. Stars look like they're all lined up next to each other, but in fact, it's just because they're all that way in our line of sight. But if you were looking at it from a different angle, they would look very different. A good example is the belt of Orion, which looks to us like a line of stars all right next to each other. But if you changed the angle of your point of view, which means you got to get in a spacecraft and warp 6 for a few days, you would see that it's actually a very different orientation when viewed from a different angle.
Yeah, someone once pointed out to me that if, when we look at these dense globular clusters, if Earth was located in the center of one of these dense clusters and we looked up in the night sky, we'd see about the same number of stars that we see now, except they'd all be brighter. But it wouldn't be like this giant glow covering the sky. It would be pretty similar to the night sky that we see here, except all of the individual stars would be brighter.
Yeah, there's different opinions about that. There are a lot of folks feel like because there's so many stars and they're so close, you actually would not have a very dark night sky. You'd have a lot of stars close to you, and the combined starlight would make it more like how things looks right after dusk. In fact, there is a book by, I think it was Isaac Asimov who wrote it. It's called Nightfall, and it's a science fiction story about a imaginary planet that's orbiting around a star in a globular star cluster, and they never have a nighttime except once every 100 years. So, and that's when all the stars happen to line up just right.
Well, we're not going to know unless we go there. So
that's right.
I'll put down a bet, and we'll send John. He'll let us know.
Yes, as soon as we get warp drive invented, we'll
coming up right now. Jupiter and Saturn, you're gonna have to wait till later in the summer. We're not ready for those yet. The same geometrical limitations that we.
Although I think if people hang around until about 10:20 or so,
we can get Jupiter.
Should be able to see Jupiter. So give us another 15 minutes and we should actually be able to point the telescope at Jupiter.
All right, we'll see how it looks then.
Yeah, it'll be our first view of Jupiter this year. And if you go outside and look, you can see Jupiter in the southwestern sky. It's very bright. It's actually the brightest object that you see right now in the southwestern sky, southeastern sky. Thank you. Southeastern sky. And if you look, you'll see to the left of it about the width of 3 fingers. if you hold 3 fingers arm's length, and to the left of Jupiter, you'll see a fainter but still pretty bright star. That's actually the planet Saturn. So Saturn is up as well. And later on this summer, they're going to be well positioned for us to look at both of them with this telescope. And then Mars comes up around midnight or so, and it's a distinct orangish red color, and it's pretty bright as well. So if you're up after midnight and you look off to the east, you'll see Mars. What's interesting, something that astronomers are looking forward to, over the course of the next several months, Jupiter and Saturn will get closer and closer to each other. Jupiter orbits the sun closer than Saturn does, and that means Jupiter orbits faster than Saturn does. So over time, Jupiter is going to catch up with Saturn from our point of view. And in December of this year, late December of this year, the two will be so close to each other that we'll be able to point our telescope at one and see both of them in the same field of view. So that's going to be something to look forward to. You know.
So there will be thousands of photographs like that on Facebook.
Yeah.
of all different quality and composition.
And we'll all better.
Yeah. There was another question. Is Sirius a possibility tonight? No, I'm not very serious tonight.
No.
Or Betelgeuse. Well, a couple of things about that question. First of all, those are winter constellations that those stars are in. So we'll be able to look at Orion, and we'll be able to look at Canis Major at a different part of the year. Right now, those are not up in the night sky. The other thing is we rarely look at individual stars unless there's something particularly visually distinguishing about them. So we may be looking at certain double stars, and that would be a reason to point at a single stellar object or a double stellar object. But looking at Sirius isn't going to show us much, and looking at Betelgeuse is just going to be the red version of not showing us much. It'll just be a bright red dot. All right, what's next?
Well, I don't know. We need to kill about 10 minutes here until Jupiter gets far enough over. Jupiter is right next to the dome. We would be able to look at it right now, but as a lot of you may know, we have 3 observatories up here. The largest of our 3 observatories holds our 20-inch refractor, which we call Rachel, and it has a big 40-foot dome. And that dome is to the southwest of the observatory that we're in right now. And it's so big and so high that it actually blocks our view of the southwest sky up to about 25 or 30 degrees above the horizon. And so right now, Jupiter is just emerging from behind the dome. And so we have to wait until the Earth rotates a little bit farther so that Jupiter gets far enough clear of the dome to where we can point our telescope at it. So we're kind of killing time here.
Yeah, we always have to wait for the Earth to rotate.
Yeah.
Why don't you put it on the Trifid? That's reasonably close.
Hang on just a second here. Let me mute.
Yeah, it's really big and we can't see it with this telescope. The North American Nebula is a very large area of the dense part of the Milky Way galaxy that is a very well-known star-forming region. And yeah, it's in the constellation Cygnus. It's quite beautiful. There's a lot of great photographs of it. It's not anything that's easily seen with this particular instrument because we have such a long focal length, we can't really get the whole thing in a field of view. We can just get little bits and pieces of it. It's a great target for some of the other telescopes here, but not for this one really.
There's also questions about checking out Uranus and Neptune. Neither one of them will be in the sky.
Yeah. We gotta wait for planets. We have a dearth of planets at this time of night right now. So later in the year, we'll be able to show you some. Okay, we're slewing now to hopefully the Trifid.
M11 was also Alan.
All right, I'm going to do a quick. Actually, I'm not going to do a quick shot. I'm going to go for 30 seconds here, and hope for the best. I'm going to take my chances.
I'm not even seeing much.
Yeah, it's not that bright, so we'll see if we got anything. So you guys can now see what taking astrophotographs is really about, which is a lot of fumbling around.
And waiting.
Yeah.
Not to mention a lot of cables.
Yeah, well, there you go.
Oh, there it is. Oh, yeah. Excellent.
Right.
Yeah,
let me see if I can play with the spectrum on this a little bit.
We need to go east a little bit.
Are you moving it?
Yeah.
There we go.
I just moved east a little bit.
Okay, I'm going to take another shot. Ready?
Go.
Okay, good. All right, so what you're looking at here, and actually you could even see some of the color, which is pretty cool. The Trifid Nebula is another really well-known nebula, kind of a favorite photographic target. It's another star-forming region, and it has these interesting gas clouds in the foreground that make kind of a spider shape here. And let's see what this next one comes out to look like. Hopefully,
are you shooting 30 seconds?
Yeah, there we go.
Oh, perfect.
Yeah, that looks pretty good. And that's in
no, Sagittarius.
It's Sagittarius. Sorry,
just above the top of the teapot.
Right.
Yeah, we're actually looking almost directly into the center of the Milky Way galaxy. Yeah, obviously you can't see it, but the central hub of the Milky Way is actually in the same line of sight as the Trifid Nebula. So if you were out at a very, very dark location to where you could clearly see the Milky Way, and you looked to the southern sky this time of the year, you could actually see the bulge, the central bulge of the Milky Way, and that's right where we're looking right now.
We have some more good questions. Welcome, Daryl. First time on Facebook today and just saw this. Well, I'll tell you, that's a lot better than my first Facebook experience. And congratulations for finding the right place to go on Facebook. What are the chances of socially distanced in-person viewing parties this year? I got to tell you, next to zero. Yeah, the way things are going. We're still at the, we don't know where the peak of this thing is. We're not in the right side of this curve. But there are no plans at this time to reopen the telescope deck.
Yeah, but stay tuned though.
Yeah, stay tuned. Just stay in touch.
Discussions of doing very small group observing sessions where we would make you all stand very far apart from each other and kind of come in and look one at a time. So
yeah, and we'd have to clean the eyepiece in between each use.
Right.
Or I'm going to go in the like I've been telling people, I'm going to go into the business of disposable eyepieces. Yeah. For this very reason. Tony was mentioning that Epsilon Lyrae is a lovely double-double in constellation Lyra, and yes, it is, and that would be a nice thing for us to look at one night, but it won't be tonight.
Yeah, keep in mind we have a fairly small field of view with this telescope.
Yeah. Double stars, we will have a little bit later this year. We'll do some more with double stars. Last week we did show Albireo because it had the nice red and or gold and blue colors. And there's a few other double stars that are quite remarkable to look at, which we'll be looking at this year. So stay tuned. Just not tonight.
Let me, I'm going to mute here for a second. I'm going to go check and see if Jupiter.
Yeah, we're Jupiter spotting here. Yeah, I think it's just peeking out. No, not yet.
Yeah, too early.
It's up, but it's,
I mean, I can, if I stand here, I can see it, but if I stand over here, it's still got a ways to go.
yeah, we looked out the window.
Oh, I can see it from here.
Oh, yeah. It's gonna be a while.
Yeah. Well, it's up there. So you see all those.
Yeah, that was.
You see all those dark lanes in the Trifid. Those are just dense clouds of gas and dust, and that's where new stars are forming. There's also some dense clouds around the periphery of it. You can kind of get a sense of that down in the lower left. And again, this is how stars form, from dense clouds of gas and dust that are condensing. And they don't condense uniformly. They condense in little knots here and there. And those little knots eventually become new stars. If you're out in a very dark sky location, up in the mountains or somewhere where you can see the Milky Way clearly, as you look across the Milky Way, you'll see what looks like gaps. And those are actually not gaps. They are huge clouds of gas and dust out in space that's actually obscuring your view of the Milky Way stars that are beyond them. So they look like gaps, but they're actually giant molecular clouds where new stars are forming.
I've gone ahead and I've put a more processed image of the Trifid behind my head.
There you go.
In the little square where I'm talking. And that way you can kind of see what the entire nebula looks like. And you can see that there's an area in the upper portion that we're looking at right now is mostly hydrogen gas, whereas the lower portion is an awful lot of oxygen, which is giving it the bluish color. And I don't know what that thing is that's coming out of my head, but it's not, it's not real.
Yeah.
Yeah. It's a gas cloud coming out of my head.
Yeah. Now the image that Richard is showing you up there behind his head is actually a.
Oh, it's a telescope. That's what. If I move the back, the whole image disintegrates into a telescope. That's pretty interesting. So I'll put my back here so you can see the Trifid.
Yeah. So, that's a wider field of view shot. So that would be something taken typically with a smaller telescope.
Yeah.
With a much wider field of view than we have with Nellie, our 36-inch telescope. There's no such thing as a perfect telescope. Some telescopes are good for astrophotography of large objects in the sky. Others are good for astrophotography of small objects in the sky. And some reproduce colors better than others. It just depends on what you want to do with the telescope.
Yeah,
so
that's absolutely true.
And also how long you want to sit there and freezing while you're taking astrophotos.
That is a factor. The smaller the telescope, the more you freeze.
Yep.
Yeah. That is absolutely true.
Well, I think it's going to be a while before we're able to see Jupiter yet. So
let's see if we have some more questions. I'm going to turn off this. That might be possible.
Look for
no,
what?
That's in the Ursa Major.
M82?
Yeah.
Yeah, we can go to M82.
Okay. Let me get rid of this virtual background.
Yeah, we'll do it in a couple of hops here so we can.
Yeah, we definitely need to do more than one hop on this, I think. No, it's right there. Yeah.
What are we looking for?
M81 or M82.
Okay. All right, I'm going to go back up to Roswell Hague to synchronize. So I'm a slew.
Okay, I'll go back into live view here. Okay, M81 and M82, which was a request from Facebook. Those are both galaxies, and they're spiral galaxies. They're about 14, 15 million light years away, something around there. Did I get that right?
Okay.
Okay, there you go.
Yeah, that's dead center. We're good. Go to the next top.
All right. M82 is a little bit in the western sky, right?
Yep.
Yeah.
So we'll have to watch the chords here.
You have Arcturus over there.
Yeah, you can put it on Arcturus as a calibration.
Or even Mizar.
Battery here is done.
Yeah.
Mizar would be good because it's easy to identify.
Okay, here we go. Sync on another star. Here we go.
All right.
Where are you going?
Alcade. It's the N star. In.
Okay. Pretty close.
You got it.
Okay. A little bit.
Okay.
All right. You sync on that.
Sync on that. Let's go to M82. And here we go. Way up north.
Should. We're there?
They're there.
All right. I will take a shot.
Look,
All
it looks just like the Trifid.
No, there's no way. I haven't figured out a way to blank the previous image yet. Everybody gets excited that, oh, it's the same thing we looked at before. Okay. Oh, that's nice. Good. Okay.
Yep. The Cigar satellite or galaxy. What was that, 30 seconds?
Yeah.
Yeah. I'm going to move a little bit east and maybe do a little bit longer exposure.
Sure.
Although that's pretty good.
Yeah.
So we're looking at a galaxy almost edge on here, and there's a lot of dust in it. A few years ago, there was a supernova explosion in this galaxy. Now you see the star that's just kind of down below the galaxy and in the center. That is actually a foreground star. That is a star that's in our own galaxy. And so it's pretty bright. The supernova star in M82 was actually brighter than that star. So you had a star that was millions of light years away, brighter than a star that was only a few hundred light years away. That's the nature of supernova explosions. When they occur, they put out a tremendous amount of light, and at times they can actually outshine all the light from the rest of the galaxy. But it has since faded away. So M82 is back to being normal. We think that on average, there's about one supernova explosion every 100 years in any given galaxy. Fortunately, there are so many galaxies out there that we see supernova explosions in some galaxy almost every week.
Except what was the one with that supernova that we looked at recently beats all the odds, though, because it's had like 8.
Oh, yeah, yeah. Well, on average, you know.
Yeah, on average. We can take a look at M81 also. It's right
Yeah, M81 is very close by. So, did you reshoot this image?
No, I just stretched it a little bit.
Oh, okay. So let's sync and then go to M81. Not M811, M81. All right, here we go. Bode's Galaxy, or Bode's Galaxy is actually what it's called.
Let me know when
It should be there. It's not a very big move.
I didn't even hear it. It's a very quiet telescope.
Sometimes.
Except when you're yelling at it.
You know, what we forgot to do tonight is turn on the fans. Should have done that earlier. So inside Nellie is a mirror. It's 36 inches in diameter and it's 5 inches thick. It's a big, huge chunk of glass. And on hot days like today, you know, there it is. So it's a little hard to see the spiral around it. You see the bright core.
Yes, core is real obvious. I could try a longer exposure.
Yeah, while he's doing this, let me just finish up my story about the mirror. That big chunk of glass, on a hot day like today, it gets very warm, and glass is very slow to lose its heat. And so, you know, the sun goes down and the glass is still pretty warm. So what we do, we have fans installed on the side of the telescope, and the fans blow air across the surface of the mirror in what we call laminar flow. And so until the mirror gets down to the air temperature of the nighttime sky, you want that laminar flow, because what would happen otherwise is you would get a layer of warm air directly above the mirror, which would cause distortion. If you imagine looking close to the ground over hot concrete or hot asphalt, you'll see all these ripples in the air. And we would get the same thing above our mirror if we didn't do something to cool it. Now, we did wait until 9:30 to start, so the mirror cooled a little bit, but it's likely that had we run the fans right after the sun went down, by the time we were ready to view, the mirror would have been a lot cooler. So we'll have to remember to do that next week. Yeah. Yeah, it looks like that's about as good as we're going to get.
Somebody had jumped in and was wondering if we were looking at Jupiter. No, this is a M81, which is a spiral galaxy in Ursa Major, and it's about, I was going to say 12 to 15 million light years away, something like that. May even be more. But we're going to see if Jupiter is visible yet. We're just kind of burning time to see if we can. Is it? Think we're there? Yeah, we'll give it a shot.
Yeah.
See what we can see.
Okay, so we're going to go all the way back the other direction.
We can take hops along the way.
I'm going to take a stop.
Yeah.
Alpha.
Just do Jupiter.
Well, yeah, I suppose. Unless it's out of the field of view, it'll make it difficult. Oh, you'll be able to see it in the viewfinder. Yeah. Okay. Yeah, just go all the way. Or is it too late? Too late.
Wait, we're going to Alpha, which is
right.
in Corona Borealis.
All right, pretty
nice
close.
And bright.
Bring it center. All right, that's good.
Okay, you want to just go straight to Jupiter?
Yeah.
Brave soul. Here we go.
Oh, okay.
All right. We got to go east a little bit.
Don't center it, though. Stop right there and move it up a little bit on my screen.
Okay.
I want to make sure that we get a couple of the moons there.
Yeah, I see one there.
I see two.
There's, I see 3 in here.
All right. Well, it's not in the view of the camera, though. Okay, so this is live view right now, so we're not manipulating the light curve.
It's actually a little overexposed.
Yeah, it is. So I'm going to actually change the ISO, see if we can do something better with that. Give it a sec, see if we can do that. I don't think it changes.
I see 2 moons.
Hold on. Yeah, you can't change the ISO on live view. Yeah, you can see 2 of the moons, but let's try doing an exposure then. I'm going to do.
That bright one is probably Callisto.
Yeah, I'm going to try experimenting with what the right shot
There's
is.
one way out that might be Callisto. I think one of them must be.
Oh, you found him.
Yeah. Okay, let's go to 200.
Good view.
So Jupiter has 4 bright moons and about 80 others. The 4 bright moons we call the Galilean moons. They were first observed by Galileo in, I believe it was 1610. They're Europa, Callisto, Ganymede, and Io. Io is the closest of the 4 to Jupiter, and it orbits so fast it makes a complete orbit around Jupiter every 2 days.
Yeah, we're not gonna unless I did like video and stacked it. We're not gonna get much in the way of detail from this. But you can see it's a ball.
Let me move it around, see if we can see anything else here. Oh, are you in live view?
Yeah. No, I'm not on the live view, but I can
okay.
keep live view. Let me. There we go.
Oh, there's another one. Actually, 2 of them are right next to each other.
Yeah,
right?
yeah.
Yeah, so that's probably Europa and Io.
And there's a bright star. It looks like a moon. That's what confused me looking in the finder.
Yeah, but that's not in the field that we're looking on. Yeah.
So Jupiter is, easy to see naked eye, certainly with a pair of binoculars. If you have a good pair of binoculars with a large enough aperture, say 50 millimeter lenses on it, you might even be able to see the moons. They would be very close in a binocular field of view, but I have personally been able to see the moons. That was interesting.
Yeah. That's me randomly clicking on things.
So we had our first view of Jupiter. Maybe we can do some different imaging next week.
Yeah, we're going to be experimenting with some different cameras and see whether using a different type of camera might be better for this type of thing. So,
and naked eye through this telescope, where you're just looking through the eyepiece, you can clearly see details on Jupiter. Jupiter rotates very rapidly. It's completely covered in clouds. It's what we call a gas giant. And as it rotates, high and low pressure areas within the clouds get wrapped all the way around the planet. And we see those as dark and light stripes on the planet. When we have kids looking through the telescope, we tell them to look for the beach ball out in space, because that's kind of what it looks like. Now, if you have higher magnification, you see more details within those stripes. There's actually swirls and eddies and all kinds of additional features. And then, of course, if you catch it at the right time, you can even see the Great Red Spot, which is a huge cyclone in the southern hemisphere of Jupiter.
Right in the middle right now.
Is it? Okay, change your exposure. We got to see the the Great Red Spot. So Jupiter, because it's so big and it's a gas giant, it has so much mass, it actually rotates very rapidly. The average length of the day on Jupiter, the average day on Jupiter is about 9 hours and 50 minutes long. So it rotates very rapidly. So the Great Red Spot is only there for maybe 4 hours or so at the most. And so you got to catch it at the right time in order to see it.
Okay, well, this is about as good as we're going to get. That's better than I thought we could do. And I see the red spot. It is right here.
Yeah, it's hard to see. Actually, we can see it better looking visually through the telescope. One technique that astronomers often use is, rather than putting a still camera like this on the telescope, they put a video camera on the telescope. And they just shoot about a minute or so of video. And each individual frame of the video is pretty faint. But what they do is they go through and pick out the best frames, and you may end up out of 3,000 frames, you may end up with only 50 or 60 that are really good, sharp images. And then you stack those together, and it produces some very high quality images of the planet. There are a few people around the world who are extremely good at that. One guy is a British amateur astronomer named Damien Peach. Another one is, I think he's in the Philippines. His name is Christopher Go. These guys have just really perfected the technique for doing this. And they do it with a video camera. Are you taking another image, or you just?
I'm just snapping them until I get one that gets a good pause in the scene. So this is one of the better ones. You can certainly see
yeah, your mic is off. Your mic is off.
Yeah, I was taking a series of them to find one that was standing out in what is not great seeing tonight. And at least we could see the bands and the red spot. And the red spot, like I pointed out earlier, I get my mouse cursor, is right there. And you could, maybe on Facebook it may be too difficult. By the time it gets to Facebook, a lot of this gets washed out. Yeah.
Yeah, so Richard was talking about something called seeing, and I expect most of you know what that means, but for those who don't, seeing is a term that astronomers use to refer to how well we can see fine details at a given time on a given night. We are looking through a thick layer of clouds. In fact, because Jupiter is so low in the sky, we're looking through, or not clouds, but air. And because Jupiter is so low, we're looking through even more air than it would if it was high in the sky. And that air is constantly changing. You get thermals in the air, you get wind blowing. All of that causes continuous changes in the density of the air that we're looking through.
I can put it back.
And because of that, the image will appear to go in and out of focus. If it's a very windy night, it's really bad. It just looks like the planet is boiling. And so what we do when we're taking images like this is we try to just collect a whole bunch of images and then sort through them until we find the best of them, and then use those to produce even better quality images. Now, you notice those two moons that are close together, they're now a little bit farther apart. Remember how I told you, one of those is Io. Remember how I told you that Io orbits around Jupiter very rapidly, so much so that if you wait just a few minutes, you will notice a definite difference in the position of Io relative to the other moons and the stars in the background.
I'm not sure yet. Hold on.
Yeah, just
I know everything's getting blown out here. Hold on for a sec.
So Richard is changing camera settings to try to improve. That's actually a little better.
Yeah.
Now I can see the red spot pretty clearly.
Yep. I'm going to take a series of shots here and wait till we get one that hits the seeing at the right place. There we go. That's not a bad one. Yeah, the question that somebody asked is, how come it's not really sharp and clear? And aside from the seeing issues that Gerald talked about, and somewhat related to it, is that's why we use video for capturing planetary images, because it may be 1 out of 50 frames that is worth preserving, and all the rest are kind of blurry because the mirror's cooling off or because the atmosphere is boiling. And then you take all of those excellent frames, only use those and stack them together to get as much detail as possible. So I was just taking a bunch of shots until one stood out.
Are you still taking shots?
No, I stopped.
Yeah. Why don't you do it again? I just changed the focus slightly. I don't know if I made it better or worse.
Probably made it worse to keep this focus. Yeah,
Okay.
that's a good one.
Yeah.
There we go. So
you see what I mean? I took about 10 shots there until one just kind of jumped out as being more clear than the others. And if I had been taking video, that's one of the ones I would have preserved. So I hope that kind of gives you an idea. On Facebook, I don't know whether it's really, it's not too bad.
Is there a way for you to crop and zoom in on this? Or,
Not, oh, yes, I can maybe. Hold on, let me try that.
No,
No, it does not allow for that.
Oh, well.
Yeah, there's a zoom button, but it doesn't seem to really do anything. So I'm gonna make that a no.
Okay. All right. Well, we promised Jupiter, and we finally fulfilled our promise. Yeah.
We delivered on all our promises.
Yeah. There we go. I guess it means we get reelected, right?
We get reelected. That's right. Oh, okay. Sharon says she can see the red spot now. So there's people who see it, and people are seeing the dark band in the northern hemisphere. See, it's really mostly a matter of me figuring out how to use the software properly, and now everybody can see that. Cool. I'm glad you all enjoyed that.
Well, let's see if there are any more questions.
Yeah, we'll hang out for a few more minutes to wait for more questions, and then we'll see you again next week. Yep.
So John Curry is over there. He's monitoring questions for us. I know it's kind of late for everybody. It's almost 11 o'clock, which is, early evening for us astronomers. But for normal people, it's probably time to go to bed.
Yeah, we are not normal people. Yeah, someone asked if the moons will have moved since we first showed them. Not significantly. They will move a little bit. If you're watching Jupiter's moons, especially if they are in a part of the orbit that makes them appear that like they're close to the planet, then you can really see the motion of the Galilean moons. It's much harder to detect when they're further out like they are tonight. It's just the four, whether it's a pair of binoculars or a 36-inch telescope, all we see are the four moons. Now, if we're doing photography, it might be possible to see additional ones in this aperture. I don't know.
Yeah. One of the cool things to see, and you have to time this just right. Right now, Jupiter is not directly opposite the Earth from the sun. So the sun is actually hitting it at a slight angle. It doesn't look like it in this image, but it's actually hitting it at a slight angle, which means the shadow of Jupiter is not projecting straight back from it. It's projecting a little bit off to one side. And if one of the moons goes around behind Jupiter and gets into that shadow, it doesn't emerge at the limb of Jupiter. It emerges when it comes out of the shadow. And it's a really cool effect because you'll be looking at Jupiter and it's all dark around it. And then all of a sudden a moon appears, not at the limb, but some distance away from the limb as it emerges from the shadow. It's a pretty cool effect. And then another thing that's interesting to see, the moons, their orbits are actually aligned so that we are seeing their orbits almost edge on. And because of that, when the moon swings around in front of Jupiter, it will cast a shadow on Jupiter. It will actually pass in front of Jupiter to where it seems to merge with Jupiter. But then it casts a shadow on Jupiter, and we can actually watch the shadow moving across the surface of Jupiter as the moon makes its orbit around Jupiter. So some pretty cool things to watch when Jupiter gets up high enough for us to view it and watch it over a long period of time.
All right, question is please show us Saturn. We can't, because we can't see Saturn from this telescope right now.
No, it's very close.
Yeah, it's going to have to wait till the next time.
Yeah.
Yeah.
I can see it right here. I'm standing right next to it.
Well, we could do it next Friday.
Yeah, let's do it.
Yeah, well, next Friday. Yeah, we're going to wait because we're reaching the end of our time slot,
we're supposed
and our commercial sponsors
yeah, right.
don't pay past 10:55. The other question is, do you guys change your sleep schedule so you're awake during the night and sleep through the day? I just get grumpy. And I'm awake the next day. Yeah, I unfortunately have a day job. I can't go see my customers.
Yeah, I have a day job. I have a day job too. I'm an airline pilot.
You seem tired today. You sure you want to fly the plane, Gerald?
No problem. That's what they made an autopilot for. You know?
Yeah, that's what the autopilot's for. Yeah. All right.
So John, are you looking at Saturn? How close is it?
Yeah, I see it. It's coming. I can see it right here. Yeah.
I can't see it right here.
Oh.
It's right on the edge of the great stone.
So I bet you if I point the telescope at Saturn, we can watch it emerge from behind the dome, right? So we should do that here. Hang on a second here. We might as well have some fun, right?
All right, I'll start. I won't be a party pooper.
Yeah. All right. So we're going to slew the telescope to Saturn, but Saturn right now is behind the dome of our 20-inch telescope, but it should emerge in just a few minutes.
I see a little bit of Saturn.
Oh yeah, there it is.
Hold on, let me
so go live view and just.
It's being eclipsed by the other dome, but there's enough light coming in.
Yeah.
Hold on, let me get to.
Are you in live view?
Hold on, no, I'm going to do exposures here. Oops,
yep.
There we go. Okay, so a second too much. Let me go to 1/10 of a second.
Look at that. The planet with rings around it.
All right. The exposure, right?
There you go.
All right.
So.
Make it a little bit brighter. Let me up the ISO to 200. Yeah, I could hear them coming from Facebook. All right.
Now, when we look through the telescope with an eyepiece on there, we can actually see more detail than this image is showing. The eyepiece, there's an eyepiece that we can use that gives us a much smaller field of view, which makes Jupiter or Saturn look bigger in the eyepiece. And you can clearly see the rings. You can see bands across Saturn's surface. There are some gaps in the rings, one notable one called the Cassini division. We would be able to see that looking naked eye through the telescope with one of the eyepieces that we regularly use. So
this is using what, about probably a third of the mirror right now. Not even. Yeah, because we have a finder scope mounted right in the middle of the scope, and you can't even see it through the finder scope yet.
Yeah, so
we're some little piece of the mirror on the 36 is able to just catch the light from Saturn, and it's bringing it to a focus.
Yeah, remember we've got a 3-foot diameter mirror, so part of that mirror is seeing Saturn, and part of it is not. And one of the things that the way the mirror works is every point on the mirror sees the same object unless there's something blocking it. But they all see the same object and bring the image to the same point on the camera. So even though only a portion of the mirror is seeing Saturn, that portion is bringing the full part of the image that it sees to the eyepiece or to the camera. So as what happens is the Earth rotates and more Saturn gets out from behind the dome. The image will get progressively brighter as more and more of the mirror brings light to the same point on the camera.
It's 4 ring diameters.
Yeah, I don't see Titan.
You can tell from that picture which way.
I see some hot pixels, but I don't see Titan.
There's a couple of.
Yeah, we're looking for the moon Titan right now.
Yeah, we may be out of the field of view.
Yeah.
Yeah, I can just barely see them in the finder.
That was a blurry one.
Well, we weren't expecting to see Saturn, so this is kind of a bonus for the evening.
Yeah.
And we're almost up at our 11 o'clock stop time. So certainly over the next few weeks, if the weather cooperates, we will have lots more opportunity to see both Jupiter and Saturn. So please join us again next week and, pray for good weather, and we'll get a chance to see these things again.
All right. Good night, everyone.
Good night.